Okay, so what we have seen is that if you are thinking in terms of vacuum, in vacuum, there is a possibility of having electromagnetic waves. So at least it doesn't, having electromagnetic waves doesn't contradict our laws. Of course, still we need to study their properties if we can create them, and we have to study how we can create them. Any questions up to this point? Now let us look at possible forms of these waves. Now by possible forms, we had just said that, well, since the sum of two waves is itself a wave, we can only look into harmonic waves, waves that we can write in terms of sines and cosines. Or even better, we can work in terms of waves that can be written in terms of exponents, exponentials, complex exponentials. So let's see if there are waves of this form. E0 times e to the power I k dot r minus omega t. We know that any wave we can just write as sum of such terms. Just remember your Fourier analysis course, Fourier analysis section. Any function you can write as a sum of these things. Well, electric field is a wave. Let us also choose the B field. It will be B0 e to the power I k dot r minus omega t. Well, the B field, we just said that if you just look at our equation, since there is an electric field that is changing in time, we should also have a B field that's changing in time at the same time. Well, let's keep it quite general for the time being. Maybe the electric field will have some wave vector and some frequency, and the magnetic field will have some other wave vector and some other frequency. Maybe. Let's leave it as a possibility. Now, of course, we will need to determine if there are any conditions on these numbers. So is the wave vector and the frequency, they are independent of each other? Can they take any value? Is the wave vector in the E field and the wave vector in the B field, are they related to each other, or they are completely independent? So those things we should determine it by using the Maxwell's law. Because whatever the electric field or the magnetic field you have, they should always satisfy those four equations in vacuum. So what should be properties of these numbers or vectors such that this electric and magnetic waves satisfy my Maxwell's equations? So let's start with the first one, divergence of the electric field. What is the divergence of our electric field over here? It should be 0, but in terms of this is our electric field. Let us calculate the divergence of this thing. We will be obtaining the divergence in terms of E0, K, and maybe omega. Then we should set it to 0. It gives us a restriction on these numbers, vectors and numbers. We are in vacuum. We will stay in vacuum. So let's see, what is the divergence of E del x Ex plus del y Ey plus del z Ez, if you write it explicitly? Let me just calculate one of them, just this term. This will be equal to del x. Well, Ex is the x component of E0 times e to the power I kx times x plus ky times y plus kz times z minus omega t plus the other terms. Well, the x-dependent part is only this one. If you take the derivative, it just has I kx times the rest. So this is equal to I times kx times E0x times e to the power I, etc., plus the remaining terms. This will be I. Well, you see, if you repeat the same thing for the y component, you will have ky over here and E0y over here. For the z derivative, the last term, you will get kz here and E0z over there. So it is kx E0x plus ky E0y plus kz E0z times e to power I, whatever, all that exponent. And as your friend has said, the divergence of the electric field for a physical electric field, it should satisfy our Maxwell's equation, so it should be 0. But you see, this combination over here is nothing but the scalar product of the k vector and the scalar product of the E0 vector. This should be equal to 0. So that is one condition we have on k and E0. Well, let's go back over here. What is the velocity of this wave? In the one-dimensional case, the velocity, the speed was speed of the wave, we defined it as in terms of this omega and k. It was omega over k. This was in the one-dimensional. If you just look at the units also, omega has the units 1 over second, k has the unit 1 over the length, so omega over k also has the correct unit. And if you just review our previous discussions on Monday, you will see that this is the wave. And it is moving in the three-dimensional case, the velocity vector will still have the same magnitude, and it will be moving in the k direction, k hat direction. So the velocity of the wave is in the k hat direction. Now, what is waving? It's the magnitude of, it's the electric field that is waving, and the electric field is waving in the E0 direction. This is the polarization of this electric field, in a sense. And what we had seen here is that polarization should be perpendicular to the direction of k, which is the direction of velocity. So we have the electric field that is fluctuating. Its fluctuations have to be perpendicular to the direction of the velocity of the wave. It is this law, this result. So what do we call these kind of waves? Transversely polarized. So this tells me that it is transversely polarized. So this is one condition. We can create electric waves in vacuum. It has to be transversely polarized. We cannot create longitudinally polarized waves in vacuum.
Yani parçacığı şöyle hareket ettirirsem bunda bir değişim olmuyor mu buradaki elektrik fiili?
Well, we will see the creation of electromagnetic waves. We will see that if you have this charge, if you oscillate it in this direction, there won't be a wave in the plane of that acceleration. The electromagnetic wave will be 0. There is still an electric field, but there is no wave, there is no fluctuation. There is no vibration of the electric field. It will be constant.
I didn't understand how we could find that this is transversely.
What is the definition of transversely polarized wave?
This is a wave whose particles move.
Not necessarily particles. You see, waves need not be made up of particles. But what we are talking about waves on a string.
The direction of the motion is perpendicular to the direction of oscillation.
Yes, that is what we define the transversal wave. A wave phenomenon need not have particles. Okay, these waves on a string, we call them waves, and those waves are just the displacement of what is waving is the displacement of particles. That is our wave. in this case, there is no displacement of particle. It's the electric field that is waving, that is changing in position and time. That is waving. And so the electric field has a direction. So this changing electric field will have a direction. So that is kind of waving. And plus there is a direction of the propagation of these changes. That's the velocity of the wave. And we know that the velocity of the wave is perpendicular, is in the k direction. That's kind of one of the meaning of this k vector, the wave vector. The wave propagates in the k direction. And Maxwell's equations tell me that this k vector is perpendicular to this fluctuating electric field. That's a result of the Maxwell's equations. Well, the electric field is perpendicular to the fluctuating the electric field is perpendicular to the k vector, which is in the same direction as velocity of the wave. So this tells me that the fluctuating electric field is perpendicular to the direction of the velocity of the wave. And this is the definition of being transversely polarized. Still, if the wave is moving, let's say, in the z direction, or let's say you choose the direction of k as your z-axis, the wave can still be polarized along the x-axis or along the y-axis, but it cannot be polarized along the z-axis. It's just our interpretation of this result. Which is a direct consequence of the Maxwell's equations.
Let me ask another question.
Sure.
For example, if we have a slinky and we create a transversely polarized wave, do we create the other type of
Longitudinal.
Yes.
Well, on a slinky, you can create both of them. Most of the time, you will create both of them at the same time.
Because I have tried it before.
Sure.
Both of them are created at the same time.
But even if you create both of them at the same time, you can just decompose them. You can just write it as a sum of two different waves, one transversely polarized, one longitudinally polarized. But that is not the case in this electric wave. The electric wave has to be transversely polarized. You cannot create the longitudinal polarized electric wave. At least not in vacuum. Longitudinal polarized. I mean, you see, first you need to create that longitudinal polarized wave. You cannot create it. You cannot create. Well, we will see. We will also study the interfaces. We will see under which conditions we might be able to create longitudinal waves. And if we can create longitudinal waves, let's say in medium, if we didn't study it yet, if we can create it, then this basically tells me that it cannot leave the medium. It is trapped inside the medium.
Hocam diyelim ki şöyle hani kondaktör sferi düşünsek.
We will. No, okay.
O zaman işte dışarıdan elektromanyetik dalga geldiğinde bu kondaktörün içindeki elektrik alanı düzgün olmalı. O zaman ne oluyor?
Okay, we will see the transfer phenomena also. But inside the wave, inside your whatever the shape is, if you write it in terms of a superposition of plane waves of this form, then each component has to be transversal. Well, from our general knowledge of wave phenomena, at least if we know that if we have such an equation, this equation describes waves, and the waves might have complicated forms, complicated shapes, but whatever the shape is, whatever the form of the wave is, we can always write it as a sum of waves of this form. That is what Fourier tells us. So we said that, okay, rather than studying some complicated forms, some general discussion, let's look at these special kinds of waves. Well, we won't be losing any generality, because any kind of wave we can just write in terms of these. So if all terms of this form satisfy certain properties, then we can say that the general form should also be satisfy the same property. We see that all these waves are perpendicular to the direction of propagation. So whatever you write in terms of these, if you can identify some direction of propagation, the electric field at that point of the wave should be perpendicular.
Hocam bu B0 maksimum değer değil mi?
Yes, well, let's say amplitude. E0 and B0 can be complex. But B0, the magnitude of B0 will be the maximum value of the magnetic field. The magnitude of E0 will be the maximum value of the electric field. Other questions? Well, let's see. We can just repeat the same thing that we did for the electric field for the magnetic field. So we already studied the consequence of that law. Let's look at the consequence of the divergence of B equal to 0. So what does it tell me about the magnetic field, magnetic wave? Well, the derivation is basically identical. Instead of E0, just use B0. So del dot B is equal to 0. This just implies that K prime dot B0 is equal to 0. I will not repeat the same. The derivation is identical. The forms are identical. The equation is identical. K prime is the wave vector of the B field, B wave, and B0 is the magnitude of the B wave. So again, the B wave is also transversely polarized. Both the E wave and the B wave, they are both transversely polarized.
B0 mu transversely polarized hocam?
The wave is transversely polarized. B0 is the polarization of the B field, B wave. And that should be perpendicular to the direction of propagation of my wave. Now we have two more equations that we should satisfy. Let's look at the first one. The curl of E is equal to minus del B by del T. Let me calculate the curl of E. This is the curl of E0, e to power I k dot r minus omega t. Well, let me just go back to what our derivation over here. There is a derivative with respect to x. In this line, that derivative with respect to x just becomes I times kx. If you take the derivative with respect to y, it just becomes I times ky. If you take the derivative with respect to z, it just becomes I times kz. So basically, this will be equal to, well, whatever derivative we have over here, whatever component you are talking about, it just becomes I times the k vector. So this is equal to I times k cross E0, e to power I k dot r minus omega t. Well, if you just open up the components, etc., you will see that, for example, for the z component of this thing, you will have the x derivative of the y component minus the y derivative of the x component. So it will be kx times the y component with an I minus ky times the x component. Well, that is nothing but k cross e, the z component, I. So whenever you have this operator acting on our plane wave, it just becomes I times the k vector. Well, if you just realize that, it just saves you lots of taking derivatives. Del B by del T, you see del B by del T, if you just take the time derivative, it just becomes, if you just look at above, it just becomes minus I omega prime. This is equal to minus I omega prime B0 e to power I k prime dot R minus omega prime times T. And my Maxwell's equations, that second one on the first line, tells me that this should be equal to minus this one. Or let me write it out explicitly. I times k cross E0 e to power I k dot R minus omega t. This should be equal to I times omega prime B0 e to power I k prime dot R minus omega prime t. And this equation should hold at all times, at all points. Not just at a single point, it should be valid at every point, at every time. Of course, still within my volume, within my vacuum. But you see, if you fix some point, let's say you fix R, you are looking at how the E and the B fields are changing with time at that point. Well, if they are oscillating at different frequencies, even if at a given time they are the same, they will not be the same at the next time. If they are oscillating at different frequencies. Well, that tells me that if omega and omega prime are different, if omega and omega prime are different, I cannot hold this equality at every time. But I know that this equality should hold at every time. So that tells me that omega should be equal to omega prime. So the electric wave and the magnetic wave, they should be oscillating at the same frequency.
Where did omega come from?
Omega. You see, look at the Maxwell's equation we have. I have the curl of E. Curl of E gives this term over here. The other time, on the right-hand side, I have the time derivative. Well, the time derivative of B, well, B has the same form as the electric field over here. If you take the time derivative, you have the minus omega I. That is why I have the minus I omega in the derivative. There is another minus sign over here, so it's I times omega. The B field, we started by saying that maybe it is oscillating at a different frequency. So that's why we called it omega prime. So it's I times omega prime. And since this equality should hold at every time, we said that this time dependence over here should be the same as this time dependence over here. When I'm writing this equality, I'm not looking at this omega prime over here. I'm looking at this time dependence and comparing it with this time dependence. They should have the same time dependence, which tells me that omega and omega prime should be the same. The same thing I can do for the position dependence. Let's say at a given time, t is fixed. I can consider different points. And remember, k is related with 1 over the wavelength. So if you have two waves that have different wavelengths, even if they are same at one point, they will not be same at other points if they have different wavelengths. Similarly here, if k and k prime are different, I can choose the coefficients E0 and B0 such that this equality holds at a special point, but it will not hold at every point. So if I want this equality to hold at every point, that means k and k prime should be equal. Again, in writing this, I am saying that this position dependence have to be equal to this position dependence over there for every point r. So that is why I conclude that the coefficient of the position vectors on the left-hand side and on the right-hand side, they should be the same. Now, if these two conditions are satisfied, then this exponential is the same at every point, is equal to this exponential at every point. And to make sure that this equality holds, I have to make sure that the coefficients of these exponentials should be the same. Well, the coefficient of this exponential is this one, k cross E0. This is the coefficient of the exponential on the left-hand side. Well, there's an I both on the left and on the right, so I'm just ignoring that one. On the right-hand side, we have omega prime B0. So we start with saying that, okay, the electric field, we can have a wave. For the magnetic field, we can have a wave. And now we said, okay, they cannot be independent. You see, the Maxwell's equation just relates them. Now, this is kind of the relation between the two. So if our electric wave and magnetic wave, they satisfy our Maxwell's equations, first of all, they should have the same frequency. Secondly, they should have the same wave vector or the wavelength. And thirdly, their polarization of the electric wave and the magnetic wave, they should be related with each other. Now, if you look at this relation, let's say this is our k vector. Now, we already know that the E0 should be perpendicular to the k vector. That is something we had already derived. So E0 is perpendicular to k. Let's show it in this direction. Now, this relation tells me what should be the direction of B0. K cross E, this is the direction of B0. Or let me show it in this way. These are all perpendicular to each other. So essentially, if you choose to pick up the unit vectors in these three directions, now you obtain an orthogonal coordinate system. E0, B0, and K, they should be all perpendicular to each other. Okay, so if these conditions are satisfied, okay, the electric wave and the magnetic wave, they should have the same frequency, the same wave vector. Secondly, both the electric field and the magnetic wave, they should be transversal. Those were the conditions, and they should satisfy this relation. If all these conditions hold, we had seen that they satisfy all, not all, but three of the Maxwell's equations. There's still one more left. We should make sure that these waves, if they are possible solutions, possible realizable electric and magnetic fields, they should also satisfy the third equation. And just keep in mind, since the E, B, and the K fields, they are orthogonal to each other, we can just convert this in terms of the magnitudes. This tells me that the magnitude of K, the magnitude of E0, should be equal to the magnitude of omega times the magnitude of B0. Or E0 should be equal to omega over K B0. But you see, omega over K is nothing but the speed of the wave, which we had seen that it is 1 over its C. So this tells me that E0 is equal to C times B0. So basically, the relation between the magnitudes of the amplitudes of the electric field, electric wave, and the magnetic wave, it doesn't depend on the frequency, neither the wave vector. If you just look at this relation, it seems as if E0 and the relation between E0 and B0 depends on omega and K, but in reality, it doesn't really. So the proportionality constant is always the speed of light C. But I repeat, this is correct in vacuum. Now let's look at the fourth equation, the last Maxwell's equation. Let's see if our wave equations satisfy that fourth one. Curl of B should be equal to, well, mu 0 epsilon 0, let me just write it as 1 over C squared dE by dt. This is our equation. Well, that is our E0 in the above screen and B0 are in the above screen. So curl of B is just I K cross B0 e to power I K dot R minus omega T. I already used the fact that K prime is equal to K and omega prime is equal to omega. This is the curl of B. Should be equal to 1 over C squared. If you take the time derivative of the electric wave, it gives you minus I omega E0 e to power I K dot R minus omega T. This should also be satisfied. Well, the exponentials, they cancel each other. I's, we can just cancel them. So K cross B0 should be equal to minus omega over C squared E0. Again, let's look at the magnitudes. So this is a vector equation. So if a vector equation is to hold, the vector on the left-hand side should have the same direction as the vector on the right-hand side. Let's check the directions. Okay, these are in the above screen. We have the E, B, E0, B0, and K vectors. Well, K vector is in that direction. B0 vector is towards U. So K cross B0 vector is pointing downward in the minus E0 direction. So you see the left-hand side and the right-hand side, not this minus sign, they have the same direction. They should also have the same magnitude. Let's look at our earlier solution, whether it satisfies this equality. Well, if you look at the magnitudes, K and B0 are for our earlier solution at least. So what we are doing here, we are not solving this equation, but we already have a solution that satisfies the three Maxwell's equation. Now I am checking that that solution satisfies the fourth equation. That's what I am checking. So I'm using that solution to see whether those vectors satisfy this relation. In terms of their directions, those vectors do satisfy this equation, direction-wise. Let's check the magnitudes. The magnitude of K cross B0, if you look at the above vectors, they are orthogonal to each other. So the magnitude is K times B0. This should be equal to omega over C squared times E0. This tells me that B0 should be equal to omega over k times 1 over c squared times E0. But omega over k is nothing but c. So I can cancel the c's. So this tells me that E0 should be equal to c times B0. Our earlier solution already gave us this information. Our solution does satisfy this one. So we have our Maxwell's equations. What we had done now is we found a solution of Maxwell's equations in vacuum. So that is what we had achieved. So those are our laws, the Maxwell's equations. We are claiming that they describe nature. Then we find some solutions. I write these E and the B fields. Of course, what we will be actually talking about will be the real part and the imaginary. Real parts of these solutions is our physical, electric, and B fields. So just always keep that in mind. We will be using this complex notation, but we always mean the real part. So these are, with these conditions, the E0, B0, and K vectors, they are three vectors orthogonal to each other. And the magnitudes of E0 and B0, they are related through this form. And omega, let me also write that omega over K should be C. You see, I have these. Okay, in these functions, I have these arbitrary vectors. Also, this k vector is arbitrary. Omega is some arbitrary number. They are related through these equations. The vectors, the directions of the vectors are related through this diagram. The magnitudes of E0 and B0, they are related through this relation. And omega and k, they are not arbitrary, they are not independent. Their magnitudes should be related through such a relation. If this is satisfied, then they are solutions of our Maxwell's equations. So basically, it tells us that the laws of nature does not forbid the existence of such electric and magnetic fields. Now, of course, there is the question, okay, they do not forbid, but do they tell us that they exist? Those are two different things. What we had shown is that it seems to be possible, according to our laws, that such solutions exist. But do they exist? Well, in general, as a physicist, what we do is, well, if it doesn't exist, there should be a reason for it not to exist. So that is some research that you should do. You should check it experimentally. If experimentalists, they cannot observe it, then we should try to find some reason why it doesn't exist. Definitely, the reason why they don't exist are not the Maxwell's equations. There should be some other principle that forbids their existence. But at least in the case of these electromagnetic waves, we know that they exist. Light is one of them. Now, we will be also talking about the polarization of an electromagnetic wave. This is how we define it. So each wave, in principle, can have its own polarization. But here, in this case, since once you know the direction of propagation and the electric field, the B field is already fixed. Conventionally, we define the polarization of the wave to be the direction of the electric field, or the polarization of the electric field. So whenever somebody talks to you about the polarization of an electromagnetic wave, they will mean that it's the polarization or the direction of the electric component, not the magnetic component. Yes?
Can we do the pointing vector ions?
We will see. So what we expect, we will calculate the energy, the momentum. Pointing vector is the momentum of this wave. What we expect, what you would expect, well, if the wave is moving in the k direction, the pointing vector should also be in the k direction. We will see. It turns out that it will be in the k direction. I mean, you can see it straight away. If you remember the definition of the pointing vector, it is E cross B with some coefficient. What is E cross B? E0 cross B0, that is k. So pointing vector is in the direction of k.
Hocam şimdi buna göre o zaman bize elektrik çarptığında hem elektrik alan hem manyetik alan mı çıkıyor?
Is it a wave that is hitting you?
Akım.
If it is a wave, then both of them. It's the current.
Peki boşluk içinde öyle bir elektrik alan oluşturacağım ki bana çarpacak, öyle bir şey mümkün var mı?
What do you mean by hitting you? You see, what is affecting you is mainly the flow of current, flow of electrons. As they flow, they can change the chemical composition in your body. You can create large enough electric field which will cause an electrical breakdown in your body and currents will flow. Well, that's, to start with, that's a contradiction of terms. Well, you can say that you can send a beam of electrons through vacuum or a beam of protons through vacuum. Well, that's what we do in LHC, for example. Many charged particles moving in vacuum. They also create an electric field there. Other questions? Okay, so we will continue on Monday.